Hello everybody. So we are going to continue what we started last time about the conversion from one quantity to another, and now we are going to see how to convert the mass into the number of moles. This is not a new thing, and most probably you all know what we do in this case. It's like the density between mass and volume. There is another parameter that we use to convert from mass to number of moles, and to do this we need to recall that there is a parameter that's called the atomic weight or molecular weight, and it represents the mass of a molecule or an atom, and we can find this in the periodic table. For any of these elements that we have in the periodic table, you can find some information written in each one of these squares. And from this information we will find the atomic number, which represents the number of electrons or protons, and we have the atomic mass, which represents the mass of protons plus the mass of neutrons, or the number of protons plus the number of neutrons, which is the top right number that we have here. And this is what we care about. This is what we use to relate the mass and the number of moles. And the atomic or molecular weight is can be found in the, if you have an element, then you can use the number in the table. If we have, or we're dealing with a compound, then the atomic weight or the molecular weight of a compound is the sum of the atomic weights of the atoms forming this compound. So there are some tables that have the molecular weights listed, like those we have here. We have chloroform, copric sulfate, whatever the compounds that we have in the list. So sometimes they are available to use directly without doing any calculations. But if you're dealing with a molecule that is not part of this list, you can do the calculations manually, and this is very simple. It's based on what we said here. It's the sum of the atomic weights of the atoms. So for instance, we have here water. Water is H2O, so the molecular weight of water is 2 multiplied by the atomic weight of hydrogen plus 1 multiplied by the atomic weight of oxygen. So it's 2 plus 16 is 18. For the second example, we have acetone, which is CH3COCH3. So it's composed of 3 carbons, 6 hydrogens, and 1 oxygen. So it's 3 times 12, which is the molecular weight of carbon, 6 times hydrogen, which is 1 multiplied by 16, so this is 58. So as you see, it's just addition and multiplication, so there is nothing difficult in there to calculate the molecular weight. So in case you have any molecule, whether you can get the molecular weight by finding it in tables or by calculating it yourself, it's gonna be easy to find it. And now you want to calculate the number of moles from the mass, or the opposite. So the calculations is very well known. It's very simple, and I assume that most of you are familiar with this. And the way we do the calculations is by understanding the definition of a gram mole. So gram mole is the amount that a species whose mass in grams is numerically equal to its molecular weight, which means that if you have let's say water has molecular weight of 18, so 1 mole of water is 18 grams, which is the amount of species whose mass in grams, so 18 grams, is numerically equal to its molecular weight. Okay, so this is how we define it. So the equation that we use is that N equals M divided by uppercase M. M is the mass, the uppercase M is the molecular weight. Of course, this is gram moles, this is grams, so molecular weight has units of grams and gram moles. It's not very common to use it, but this is just to make the units homogeneous. Sometimes it's in very few cases or textbooks you'd find the molecular weight having the unit of DA. DA is Dalton, which is sometimes used instead of grams per gram mole. So this is the equation that we use. It's very similar to the relation between mass and volume using density. So this is the same thing. It's also known that 1 mole of any species contains the Avogadro's number of molecules, which is 6.02 times 10 power 23. So this is the number of molecules or atoms, if it's atoms or molecules, per gram mole. So let's solve this example. It's just for practice. We have, if you have 100 grams of carbon dioxide and you know the molecular weight is 44.01, and we need to calculate these 8 requirements. So first, how many moles of carbon dioxide? It's as simple as applying the equation directly. So 100 grams over 44. This is the mass over molecular weight. So, or you can use the definition of the mole to use this as just simple unit conversion. So 100 grams, I will multiply it by gram mole over gram, and I know that each gram mole contains the molecular weight or the numerical value of the molecular weight as mass. So it's 44.01. So this is equivalent to this gram carbon dioxide. Will cancel this, and we will have only 2.272 gram mole of carbon dioxide. How many pound moles of carbon dioxide? We said before in chapter 2 that the conversion of gram to pound is the same as gram mole to pound mole. So it is just multiplying by pound mole over gram mole, and this is 453.6. It's 593, but I just put 0.6 just to make it easier for us. And then we have the pound moles of carbon dioxide. How many moles of carbon that we have? If you look at this, its carbon dioxide consists of one mole of carbon dioxide consists of 1 mole of carbon and 1 mole of O2. So if you want to know how many moles of atomic carbon that we have, it is going to be 1 to 1 ratio. So it's 1 mole of carbon is equivalent to 1 mole of carbon dioxide. So it's going to be the same. For oxygen, it's going to be doubled because we have two oxygen atoms. So in this case, it's going to be 2 gram mole of oxygen over 1 gram mole of carbon dioxide, which is 4.544 gram mole of oxygen. For number 5, it's mole of O2. So if I'm looking at this as O2s, then O2 is it's 1 O2, 1 mole of oxygen, O2, per 1 mole of carbon. So it's going to go back to the same number that we have here. For number 6 and 7, they are going to be funny or nice to know that for number 6, we need to know how many grams of oxygen atoms. So oxygen atoms that we have 4.544 gram moles. We can use this number to calculate the mass. So the mass is the number of moles multiplied by the molecular weight. This is oxygen atom, so it's 16. So it's going to be 16 gram oxygen per gram mole of oxygen. So this will give us 72.71 grams of oxygen. Now for number 7, how many grams of O2? So it's the same. This is 2.272. This is number of moles. I will multiply it by the molecular weight, but this case it's O2, so it's going to be 32. And you would find out that the mass in both cases is the same. And this makes a lot of sense because the amount of oxygen is the same, whether you put it as molecules and you count them or calculate the mass of these molecules, or you put them as atoms and calculate the mass of the atoms. The mass is always going to be the same. So whether you calculate it this way or this way, the output must be the same. This is something that you should be expecting from the beginning. Finally, how many molecules of carbon dioxide? We know that we have 2.272 gram moles, and I know that each gram mole contains Avogadro's number, so I will multiply this by this, and finally you will have the number of molecules of carbon dioxide. So this is all what we want to discuss here. Next time we will start talking about the composition and how we can define the composition. There is one last thing I forgot to mention here, which is if you have volume and you want to convert from volume to moles. We now know how to convert from mass to volume, from mass to number of moles. Now if you have volume and moles, it has to go through the mass. So if you have number of moles and you want to convert the mass, you have the volume, you need to calculate the mass, and from mass you calculate the volume. You need the two parameters, the atomic weight or the molecular weight and the volume, the density, in order to get the relation between the two of them, as there is no direct calculations for this. So I'll stop here and we'll continue next time, inshallah. See you.